Today we'll be starting off with some electrical circuit rules, which is your part 2 of your topic number 4B. We are going to understand how the distribution of current in a circuit is a consequence of charge conservation, how the distribution of potential differences in a circuit is a consequence of energy conservation, and then we're going to make some calculations as well. So Gustav Kirchhoff was a Prussian physicist working in the middle of the 19th century. He made important contributions to several areas of physics, and there are also laws named after him in spectroscopy and thermochemistry. The electrical circuit rules presented here sometimes carry his name as well. तो इलेक्ट्रिक करंट रूल इसने पहला रूल दिया था, जिसमें वो कहता है कि सारे करंट्स का अगर आप सम करोगे ना, जो कि एक जंक्शन के अंदर एंटर हो रहे होते हैं, उनका जो प्रोडक्ट होगा वो आफ्टर द जंक्शन वाले करंट जितना होगा। मतलब कि एक ये जंक्शन है, यहाँ पे 5 एम्पेयर है, 3 एम्पेयर है, 2 एम्पेयर है, इन सब का सम करोगे दैट वुड बी इक्वल टू द करंट विच इज लीविंग द जंक्शन। सो द करंट एंटरिंग द जंक्शंस, the sum of currents entering the junction is equal to the current leaving the junction. Got it? इसको हम कहते हैं किरचॉफ्स का फर्स्ट लॉ या फिर इलेक्ट्रिक करंट रूल, दैट इन ऑर्डर टू कंजर्व द इलेक्ट्रिक चार्ज द सम ऑफ ऑल करंट्स अराइविंग एट एनी पॉइंट इन अ सर्किट इज इक्वल टू द सम ऑफ ऑल द करंट्स लीविंग दैट पॉइंट एज वेल। अगर आप यहाँ देख सकते हो कि ये एक अगर हम जंक्शन लें, ये आपके पास 0.8 आ रहा है, ये जंक्शन है। जंक्शन में 0.8 में से 0.4 हैज़ गॉन हेयर, 0.4 हैज़ गॉन हेयर। लेकिन जब ये 0.4 यहाँ ज्वाइन करेगा और ये वाला 0.4 भी जब ज्वाइन करेगा इस जंक्शन में, इट इज़ गोइंग टू बी इक्वल टू व्हाट? 0.8। तो किरचॉफ्स का फर्स्ट लॉ कहता है लॉ ऑफ कंजर्वेशन ऑफ चार्ज, दैट द करंट विच एंटर द जंक्शन आर इक्वल टू द करंट दैट लीव द जंक्शन एज वेल। जैसे ये जो करंट एंटर हुए थे, ये भी 0.4 था, ये भी 0.4 था, दैट वाज इक्वल टू द करंट दैट वाज लीविंग द सर्किट एज वेल। ये अगर आप देखो कि if 0.8 is entering a junction, then the sum of currents which are leaving the junction, 0.4 plus 0.4 are also equal to the current entering the junction. तो before and after the junction जो sum of currents होगा, they are always going to be equal as well. Here you can see कि फिगर बी के अंदर भी जो हमने वो ऐड किए थे, it was all equal to 0.8 as well. So in order to conserve electrical energy around any closed loop, पहला जो लॉ था किरचॉफ्स की तरफ से, द फर्स्ट लॉ, किरचॉफ्स फर्स्ट लॉ ने क्या कहा? द लॉ ऑफ कंजर्वेशन ऑफ चार्ज। अब जो किरचॉफ्स का हम सेकंड लॉ पढ़ेंगे, दैट इज द लॉ ऑफ कंजर्वेशन ऑफ एनर्जी, कि किस तरह से वोल्टेजेस, इलेक्ट्रिकल एनर्जी, ईएमएफ या पोटेंशियल डिफरेंसेस कंजर्व होते हैं। नोट दैट अ लूप being considered might not be the whole of the circuit as well. The only requirement is that the loop is complete. And note also that the potential differences referred to here as defined as the product of the components, currents and resistances as well. हमें पता है कि जो टोटल ईएमएफ होता है, that is the sum of all potential differences of each and every component, potential difference of component 1, potential difference of component 2। अब potential difference of component 1 आप कैसे निकालोगे? I1 R1 करके। पोटेंशियल डिफरेंस ऑफ कंपोनेंट 2 कैसे निकालोगे? वही V इज इक्वल टू I2 R2 करके। ये जब आपके सारे इंडिविजुअल वोल्टेजेस आ जाएंगे और देन यूल टेक अ सम, दैट वुड ऑलवेज बी इक्वल टू ईएमएफ। गॉट इट?
जी।
ठीक है। तो पहले अगर हम इसी डायग्राम के अंदर हम इक्वेशन बनाएं किरचॉफ्स लॉ के अकॉर्डिंग टू फिगर बी, तो यू कैन सी दैट इन प्लस आउट वुड बी इक्वल टू जीरो ऑलवेज। तो अगर हम इन वाले देखें, I4 प्लस माइनस I5, मतलब कि अगर I4 ये जा रहा है, फिर ये I5 है, ठीक है, दिस इज ऑलवेज द पॉजिटिव जंक्शन, दिस इज ऑलवेज द नेगेटिव जंक्शन। ये सारे आपके पास एंटर हो रहे हैं, यहाँ पे एंटर होके वो डिवाइड हो रहे हैं I2 और I1 में। आई होप ये जंक्शन वाला कॉन्सेप्ट आपको क्लियर हो गया है। लेट मी शो यू अ स्मॉल डेमोन्स्ट्रेशन ऑफ द किरचॉफ्स फर्स्ट लॉ एज वेल, ताकि यू आर क्लियर विद द जंक्शन और कैसे हम साइन वगैरह चेंज करेंगे इन द किरचॉफ्स लॉ एज वेल। लेट मी शो यू वन थिंग एज वेल। किधर है किरचॉफ्स करंट लॉ? So can you tell me what do you understand by the Kirchhoff's first law?
फर्स्ट लॉ तो कन्वर्जेशन ऑफ करंट होता है बस।
Mm-hmm.
टोटल आपका टोटल करंट बिफोर बनता है टोटल करंट आफ्टर।
Okay,
मतलब
and potential
एंड पे
difference
वो
क्या
स्टार्ट
होता
पे।
है?
पोटेंशियल डिफरेंस एक पास होता है कि वोल्टेज एक कंपोनेंट को मिलता है।
ठीक है,
बस।
और ईएमएफ क्या होता है?
ईएमएफ स्पेसिफिकली इलेक्ट्रिकल होता है, मतलब
हम्म।
इलेक्ट्रिकल एनर्जी वो कंपोनेंट की तरफ नहीं जाता है, वो ऐसे बैटरी से बेसिकली एनर्जी, इलेक्ट्रिकल एनर्जी निकालता है बस। वो यूज़ नहीं
गुड
होता
जॉब, नाइस
है
नाइस।
कंपोनेंट्स में।
तो सम ऑफ ऑल पोटेंशियल डिफरेंसेस जो होंगे वो इक्वल टू किसके होंगे? ईएमएफ के। गॉट इट।
ईएमएफ हमारा टोटल।
गुड जॉब।
Hi guys! In this video we're going to be looking at conservation of charge, Kirchhoff's first law, and we're going to finish with a summary. So we're going to start off by talking about the principle of conservation of charge. We know that charge is a physical property of a particle. For example, we've encountered protons, and these have a positive charge. We've also come across electrons. And these are charged particles with a negative charge. So charge comes as either positive or negative. Charge can neither be created nor destroyed. So we can't destroy charge. Instead, charge is transferred by charge carriers. So these charge carriers could be electrons, for example. And electrons are charge carriers because they have a negative charge. So they're carrying a charge Q. And these electrons allow charge to be transferred. So it's not destroyed or created, it's only transferred. For example, if we had a neutral metal rod and removed 2 electrons, then the rod would become positively charged. So here we have our metal rod, and we're removing 2 electrons. So these 2 electrons are being removed from the rod. So our number of electrons being removed, N, is equal to 2. So now, because this rod has had electrons removed, it's got more protons than electrons. So it's going to have a positive charge, a net positive charge. So although the rod no longer has these negative charges, the negative charge within the rod was not destroyed. It was just carried away by the electrons. So the rod now has a positive charge, but the negative charge that it's lost is carried away by the electrons. The net charge before and after the electrons are removed is 0. So when we talk about the net charge, we mean the charge of the whole system, the rod and the electrons. So before the electrons are removed, the metal rod is neutral. So if the metal rod is neutral and we're not dealing with anything else in our system, then the net charge is 0. However, afterwards, our rod is positively charged, so it's got a positive charge now. But we've also removed these electrons, and we've removed 2 electrons, remember, so these are carrying away the negative charge. So the negative charge of the electrons is going to be equal to minus 2e, and this is because electrons have a negative charge, hence the minus, and the charge of 1 electron is the elementary charge E, but we've got 2 electrons. So the charge of the 2 electrons is going to be minus 2e. Now, if we look at the charge of the metal rod, it's going to be plus 2e. And this is because we've removed 2 electrons from the rod. So we therefore have 2 more protons than electrons. And the charge of a proton is positive and it has magnitude, the elementary charge, which is why if we've got 2 more protons than electrons, this gives us a charge of plus 2e. So we can now work out the net charge of the system. So this is going to be equal to plus 2e minus 2e. And this gives us a net charge of 0. And this is the principle of the conservation of charge. The principle of charge conservation is that the total amount of charge in an isolated system remains the same, so it won't change. For example, if we shook a beaker of ionic solution with a closed lid, the total amount of charge within the beaker would remain constant. So in our ionic solution, we have negative ions, and we also have positive ions. So before we shake it, the solution will have a certain charge. And we've also got a closed lid, and the closed lid means that we have a closed system. So we're then going to shake the solution, and while we shake it, the ions are going to move. However, we'll find that after we've shaked it, because we've got a closed system from the closed lid, the charge after shaking it is actually going to be equal to the charge before, and this comes from the principle of charge conservation. The universe as a whole can be considered as an isolated system. So our universe is also isolated. And this is because, as far as we only know our universe to exist. So there's nowhere else for all the charge in our universe to be transferred to. So it's isolated. Then the principle of charge conservation means that the total amount of charge in the universe must be constant. So since we have nowhere else to transfer this charge to, the charge in the universe has to be constant. So now that we understand what the principle of charge conservation is, we can actually apply this by looking at Kirchhoff's first law. Recall that metal wires are used in circuits to carry current. So here is our circuit. We have a battery here. Here we have a circuit component. We also have a voltmeter, which we don't have to worry about too much now. We'll look at that in a lot more detail later on. And obviously we have our metal wires connecting the circuit. And remember, this is because metal is a conductor. It's got these conduction electrons which allow the metal wires to carry charge. The current can be split by separating a wire into different paths at what is known as a junction. So we've actually got an example of a junction here. This is a junction, so we can see that the wire is splitting into two different paths. So this means that the current, so remember that current flows from the positive plate on the battery to the negative. So if we've got our current flowing through here, when it reaches the junction, it's actually going to split. So we're going to have some current going that way and some current going this way. And then after the junction, it's going to come back and recombine here. Recall that charge can neither be created nor destroyed. So we've said we can't destroy charge, we can't create charge, and this was part of the principle of charge conservation. So if a metal wire splits at a junction, then the total charge before the junction must equal the total charge after the junction, because we've just said that charge can't be created or destroyed. So here is our junction, and here we have our charge going in. And then we have Q1 and Q2, which is where our charge splits. And we've said that the charge going in must be equal to the charge going out because of the conservation of charge, which means that the charge going in is going to be equal to Q1 plus Q2. So that's how charge works in our junction. Now, since the current is the rate of charge flow, the total current before the junction must also equal the total current after the junction. So if we've got some current going in, we're going to call it I in. This current is also going to split into I1 and I2. And we've said that the current going in is equal to the current going out. So the current going in is going to be equal to I1 plus I2, because that's our current going out after the junction. And this applies for any number of wires connected to a junction. So for example, we might have two currents coming in, I1 and I2. So we've got two coming into the junction, and then the junction is split into three branches. So we have I3, I4, and I5. But again, we just said that the sum of the charge going in is equal to the sum of the charge going out. So here we're using sigma as our sum of symbol. So this means that the sum of the charge going in, which is I1 plus I2, must be equal to I3 plus I4 plus I5, because I3 plus I4 plus I5 is equal to the sum of our charge coming out. And this is Kirchhoff's first law. Kirchhoff's first law states that for any point in an electrical circuit, the sum of current flowing in is equal to the sum of current flowing out. For example, if 12 amps flows into a junction and 5 amps flows through one branch out of the junction, what is the current in the other branch? So we've been told that we've got 12 amps flowing in, and then we've got 5 amps coming out of one junction. But we want to know what's the current coming out of the other junction. Well, we've said the current going in is equal to the current coming out. The current going in is 12 amps. So this is going to be equal to the current going out, which is 5 amps, plus this unknown current I, which is what we're looking for. So now, if we just take away 5 from 12, we get what the current in the other junction is. We get that the current in the other junction is 7 amps. So this is how we can use Kirchhoff's first law. Hey guys!
तो ये Kirchhoff फर्स्ट लॉ समझ आ गई?
जी
गुड हो गया। तो अगर मैं एक पूरी इक्वेशन बनाऊं और मैं कहूं कि सम ऑफ ऑल करंट्स अगर मैं लेने किसी भी एक पॉइंट से ना इक्वेशन बनाना शुरू हो जाते हैं हम, ठीक है। अगर मैं पॉजिटिव से शुरू करूं और नेगेटिव पे आके, तो पॉजिटिव में जाओ तो ये ऐसे जाओगे, क्या हो गया, प्लस I1 प्लस वो फिर और किस किस में डिवाइड हो रहा है, प्लस I2 एंड I2 एंड I3 प्लस I4 एंड I5, ये सारे इक्वल टू 0 है। और अगर मैं इस वाली इक्वेशन को देखूं, वी कुड थिंक अबाउट द करंट एंटरिंग एंड लीविंग द रेजिस्टर। दिस इज 0.8 एम्पेयर एंटरिंग, 0.8 एम्पेयर लीविंग है। एंड इफ वी ऐड दिस टुगेदर अकाउंटिंग फॉर द डायरेक्शन, हम लिखेंगे आई इन कितने जा रहे हैं इक्वल टू आई आउट कितने जा रहे हैं। तो आई इन भी आपके पास 0.8 है और आई आउट भी 0.8 है, टोटल वो क्या बन जाता है, 0 आपके पास, गॉट इट। और अगर हम सारे इन वाले देखेंगे, I1 भी इन जा रहा है 0.8, I2 भी इन जा रहा है और I3 भी इन जा रहा है। तो 0.8 प्लस 0.4, और ये लेकिन यहाँ पे इस डायरेक्शन में ऑपोजिट आ रहा है, तो इसको माइनस 0.4 करेंगे, दैट वुड ऑल्सो बी इक्वल टू 0 as well. So it's always equal to current of sum of all currents entering is equal to sum of all currents leaving as well. And if we consider the voltages around a closed loop, और ये हम क्वेश्चंस करेंगे, वहां से आपको बेस्ट समझ आएगी इस टॉपिक की। अगर हम एक वोल्टेज कंसिडर करें अराउंड द क्लोज लूप दैट कंसिस्ट ऑफ अ सेल, वेरिएबल रेजिस्टर्स एंड फिक्स रेजिस्टर, वी नो दैट V3 must be 0.85 V as well, and all parallel branches must have the same voltage parallel to V4 as well. सेकेंड लॉ ये कहता है, फर्स्ट लॉ था लॉ ऑफ कंजर्वेशन ऑफ चार्ज, सेकेंड लॉ कहेगा लॉ ऑफ कंजर्वेशन ऑफ एनर्जी, कि जो सारे पोटेंशियल डिफरेंसेस हैं अक्रॉस द होल लूप ऑफ द सर्किट, वो सारे जब ऐड होंगे, दे आर ऑल गोइंग टू बी इक्वल टू द टोटल EMF एज वेल। कि सम ऑफ ऑल V अगर आप लोगे तो आप कौन कौन सा करोगे, V3 ले लो, V4 ले लो, दैट इज गोइंग टू गिव यू, अगर हम सिर्फ पैरेलल वालों को देखें, दैट विल गिव यू द टोटल 3 एज वेल। और हमें पता है दैट द टोटल EMF इज इक्वल टू द सम ऑफ ऑल इंडिविजुअल वोल्टेज थ्रू ईच एंड एवरी कंपोनेंट एज वेल, गॉट इट?
जी
Good. Let me show you another one about the Kirchhoff's first law as well. Yeah.
So today we're going to take a look at Kirchhoff's laws. Kirchhoff was a guy that really laid the groundwork for a lot of things that we know about electrical circuits. So he gave us a lot of equations that are very much the basis for what we need to know, and these link together things like the current and the resistance and the voltage and the electromotive force of a circuit. So we have two Kirchhoff's laws that we need to know, and the first one is very simple. It basically just tells us that the sum of the currents entering any point in a circuit is equal to the sum of the currents leaving that point. So it's very simple. Let's say you have a certain point here. If you have a certain current going into that point, then every single charge that went in there is going to come out exactly the same. So the sum of the current going inside will equal the sum of the current going outside. I1 equals I2. This is very easy, and you can also use this and link it to this. Whatever goes in from here, what is coming out will equal to this, what went in. So nothing is lost, nothing is slowed down. Remember, this is current, which is the charge over time, right? So nothing is slowed down or sped up, it stays the same. The same amount of charge takes the same amount of time to move. So we have I1 is I2 plus I3. And you could probably also kind of do this and use it for a bunch of different circuits. You can have some crazy circuit like this. Whatever goes in, let's say these are going in A, B, C, D. And this is coming out E, F, G, H. So A plus B plus C plus D equals the rest of the current. So all of it has to equal this. Obviously, this can be different from each other, but the sum has to equal each other. So once that makes sense, the general statement is that sigma I in equals sigma I out, and sigma just means the sum of everything. Now, this is an example of the conservation of charge, and this basically just means that charge is not created nor is it lost within a circuit. You put a circuit through a wire and it doesn't just randomly start conjuring up charges, and it doesn't exactly make them disappear randomly either. So that's Kirchhoff's first law. It's actually very logical and kind of easy. Thankfully, the same can be said for Kirchhoff's second law. Kirchhoff's second law tells us that the sum of the electromotive forces, the EMFs, around any loop in a circuit is equal to the sum of the potential differences around a loop, so around that same loop, right? And instead of using the word loop, you could also say closed circuit, and you will see later what that means. But here is a very, very simplified diagram of a loop. As you can see, I drew a loop over there. Basically, what it means by a loop is that it just goes around and it comes back, and it's one single track that a current or a charge could move across. And over here we have this cell, and the cell is going to be basically giving an electromotive force, right? And that we can denote by E. So there are two resistances here. We know that V equals IR. So the V, or the potential difference over here, is going to be IR1. The V, or the potential difference across this, is going to be IR2. So if you add these two together, you get E. What I'm telling you is that around this loop, you have two things that are connected in series. It's split to each component so that they can each use it. Now, for parallel circuits, it's a slightly different story, because that's not a loop anymore. As I said, a loop is basically a very simple single track that the current is going to move across. So that's what a loop is. We're going to take a look at, how to consider parallel circuits as loops later on in this video. But basically, that's all it means. It's also very, very logical. Whatever is supplied here is going to be used finished with the components, each part of the loop. So we say sigma electromotive force is sigma potential difference. If there are multitudes of batteries, then you have to add all of them together, so that gives us sigma. And if there are multitudes of components, we have to add all of their potential differences together, and that gives us sigma V. So the electromotive force of the battery equals the sum of the potential differences across the resistors or any components like a lamp or, I don't know, a diode or a fan. So this is also an example of the conservation of energy. It means that you can't just randomly summon energy from nowhere. These components will not have more energy to use than what is being supplied by this battery because it's impossible to just conjure up energy. In the same way, it's not going to be possible that you have like maybe 6 volts over here, but the total PD is like 5 volts. That means 1 volt is just simply disappearing. That's impossible. There has to be somewhere that this energy is being transferred to because energy cannot be destroyed nor created. So this is also an example of the conservation of energy. Alright, so let's try to use what we just learned to solve a couple of questions. And in this question right here, we have a circuit and it says determine the readings on ammeter 1, 2, and 3. So we have A1, A2, A3, and we have these. Now, what is very scary about this, or kind of like it throws you off, is that, well, first of all, we know that the current from here, let's take the conventional current, it flows from the positive to the negative like this. However, on this one, it flows from the positive to the negative like this. So you see that in this section where the two currents overlap, the currents flow in opposite directions. This one flows this way, this one flows this way. And so that is a little bit confusing. And here is how to solve it. First of all, you need to ignore this part and just try to solve each individual loops. So we know that over here, there is nothing. There's no resistance. Ammeters have little to no resistance, so we're going to assume that there's no resistance, which means there's 0 volts across this part, which means the entire resistance over here, we can just say that there's 0 volts from this cell, of course, across that. So what we're looking at...
So the voltage one will look next time as well. All right. So if we consider a closed loop containing the fixed resistor and the lamp as well, अगर हम कहें that the sum of EMF would be equal to sum of potential differences, they should be totally zero as well. जब उनको भी ऐड करें, they should all make zero as well, कि जो enter और leave कर रहे हैं, they are all equal to zero. Potential differences are the product of currents passing through resistances. अगर आपने component number, अगर आपने इसमें से निकालना है potential differences का, तो V is equal to IR. लेकिन आई भी आप कौन सा लोगे, जो रेजिस्टर 2 में से पास करे उसको मैं कहूँगा I2, और रेजिस्टेंस में किसके लूँगा, रेजिस्टर नंबर 2 की। तो मैं कहूँगा कि यार मैं V2 निकाल रहा हूँ, V2 इज इक्वल टू I2R2। अगर आपने निकालना है इस कंपोनेंट के थ्रू, तो इसमें से कौन सा करंट आपका पास हो रहा है, आप उसको I3 का नाम दे दो और R3 हो जाएगा। तो यू जस्ट चेंजिंग द नेम्स ऑफ देम, और आप एक एक का जब निकाल लोगे, आपने टोटल सम ऑफ द IRs निकालना है। तो इट वुड बी इक्वल टू I1R1 प्लस I1R2। अब दोनों में I1 कॉमन क्यों, क्योंकि R1 और ये देखो R1 और R2 में से करंट कौन सा गुजर है, I1 ही गुजर है। तो I1 इज ऑल्सो पासिंग फ्रॉम R1 एंड R2। तो अगर आपने यहाँ पे पोटेंशियल डिफरेंस निकालना है तो वो निकलेगा I1 मल्टीप्लाइड बाय R1, और अगर आपने यहाँ पे पोटेंशियल डिफरेंस निकालना है दैट वुड बी I1 मल्टीप्लाइड बाय R2। गॉट इट? इज इट क्लियर?
जी।
So the electric current rule is the algebraic sum of the currents entering a junction is equal to zero, and voltage circuit rule होता है that around a closed loop the algebraic sum of the EMFs would be equal to the algebraic sums of the potential differences. Electric current rule is known as the Kirchhoff's first law, and voltage circuit rule is known as the Kirchhoff's second law. Got it?
जी।